Hello everyone, today we'll be discussing how to solve a problem in fatigue, mainly drawing SN curves and determining the fatigue strength after a number of cycles. We will be examining three types of loads in determining this fatigue strength. One of them is axial loading, bending, and torsion. After solving the problem, I've realized I've answered all the units in megapascals. They are supposed to be in kilopounds per square inch. So just ignore megapascals. All the units are in kilopounds per square inch. Thanks. So this problem here says we need to draw an SN curve for bending, axial, and torsional loading of a 1-inch diameter steel bar having an ultimate strength of 110 KSI. That is really the only value we need to worry about. What we need to determine is a fatigue strength corresponding to a certain number of cycles. So our given in this problem, SU, which is 110 KSI, our diameter, machine surface, that's pretty much all we need to solve this problem. So what we need to draw our SN curve is our endurance strength and our fatigue strength. So the good news about calculating our endurance strength is that it uses the same formula for all types of loading, although the numbers will be slightly different. We have our Moore endurance limit multiplied by our load factor, multiplied by our gradient factor, which pertains to our diameter given, our surface factor, which we use this graph to calculate, our temperature factor, and our reliability factor. So one assumption we can make is that our Moore endurance limit is 0.5 times our ultimate strength, which in this case happens to be 55 megapascals. Our second assumption is room temperature, which means our temperature factor will always be 1. And our third assumption will be 50% reliability. Reliability factor will always be 1. We can use our surface factor graph to determine the surface factor. So right here we have our ultimate strength, which we were given to be 110. This line, which is the machine surface line, and draw a straight line. So what we need to calculate for each is our loading factor and our gradient factor. So for bending, we can see here, for bending will always be 1, axial 1, and torsion 0.58. And our gradient factor, we need to look at our diameter given. So we were given a 1-inch diameter. We can say our gradient factor is 0.9. Our axial is between 0.7 and 0.9. So we'll take the middle ground, 0.8. Again, this is all an assumption. And our gradient factor for torsion will be 0.9. And now we can calculate our endurance limit for each type of loading, bending, axial, and torsion. Now we can calculate our endurance strength for each type of loading. So for bending, it is our SN primed, which is 55, times our loading factor, which is 1, times our gradient factor, which in this case is 0.9, times our surface factor, which we determined to be 0.75, our temperature factor, which is 1, and our reliability factor, which is also 1. For axial loading, it's similar procedure, 55 times our loading factor times our gradient factor, which is 0.8 in this case, surface factor, temperature factor, and reliability factor. And you follow these exact same steps for torsion using its correction factors and the same SN prime. Once we calculated it, our endurance limit values were 37.125 megapascals for bending, 33 megapascals for axial loading, and 21.533 megapascals for torsion. Now we need to calculate our fatigue strength. In this case, our formula here for calculating fatigue strength is 0.9 times our ultimate strength times our temperature factor. In this case, we assumed it to be 1. So for bending, 99 megapascals. So for axial loading, 0.75 times our ultimate strength, 82.5. And our torsion, same formula as our bending, 99 megapascals. Now we can draw our SN curve. Once we have our values, we can now draw our SN curve. Now the way we draw an SN curve is we start with our fatigue strength that we calculated, and we draw a straight line to our endurance limit, which is always assumed to be at 10 to the power 6 cycles. Now the way we can draw this is starting with our fatigue strength, and at 10 to the power 6 cycles, we'll reach our endurance limit, which in this case is 37.125, so about there. Then we can draw another line connecting our endurance strength. The fatigue strength will not decrease anymore after 10 to the power 6 cycles. Now, after drawing the other two lines for axial and torsion, we can answer our questions. Now we need to find the fatigue strength at 10 to the power 6 or more cycles. Now we can see from the graph that after 10 to the power 6 cycles, our fatigue strengths are just our endurance limit strengths. So in this case, our bending fatigue strength will be 37.125, axial 33, and torsion 21.533. Now to calculate our fatigue strength at 6 times 10 to the power 4 cycles, we need to see our graph right here. So here's our 10 to the power 4 line, then 2 times 10 to the power 4, 3, 4, 5, and 6. And what we do is we just draw a straight line from here up to these points and connect it on this side over here. And we can conclude that for our bending, fatigue strength is around about 62.5 megapascals. And for our axial and torsion, it looks like they're at the same location, and it looks to be around 53. So axial and torsion, 53 megapascals. Once again, all units in KSI, not megapascals. Now, one thing to keep in mind is the type of table you use, and any assumptions you make in the correction factors will slightly alter your values. Other than that, it should be pretty close.